Welcome, everyone, and thanks for joining us today. My name is Bonnie, and I lead product marketing at Vespa. And today I'm joined by Zohar, who is our lead solution architect. The session is being recorded, and you will have a copy of recording within 48 hours after the session ends. Now, today we're going to be talking about one of the key challenges in e-commerce search, which is the signal integration problem. And you've probably experienced this as a shopper where you search for something and the results may feel stale or generic or just wrong. And the reason is almost always that the search engine doesn't know what it doesn't know. It's missing the right signals. So by the end of the session, you'll understand why that happens and how Vespa solves it with a fundamentally different architecture. So what we'll cover today, we'll start with the problem and understanding why traditional search systems fail at acting on real-world signals. Then we'll define what signals are and break them into two categories. Then we'll look at the 5 signal families and demonstrate why most systems can only act on a fraction of them. After that, we'll go deep on how Vespa's architecture changes the equation with partial updates, live machine learning model swapping, and signal fusion. And finally, we'll close with some examples. So let's start by setting the scene. Now, I'm sure, like me, many of you have purchased a gift at the last minute. So in this context, you don't just want to see the most popular gifts. You want to see the options that will be shipped to you in time. Or if you're thinking about flash sales, an item may sell out in minutes, but if it keeps showing up in search results for hours, it's because re-indexing is slow. Now, these aren't edge cases. They're the everyday reality of systems that weren't built to ingest and act on real world signals. You end up with irrelevant results, stale data, and not quite the personalized experience you're looking for. And the root cause of this is because most search engines were designed around documents, not dynamic real world events. And it's these unused signals that cause irrelevant results and stale data in your search results. Okay, so what do we actually mean by a signal? Well, for our purposes, it's any piece of information that should influence what gets returned and how it's ranked. And we split them into two high-level buckets. The first is ingestion time signals. Now, these signals get baked into the index as products are processed. Things like purchase history, click rates, stock levels, um, you know, your user personalization vectors, these are all part of the ingestion time signals. Query time signals arrive fresh with every single search request. It's the user's location, what the weather may be, what's in their cart, and which business rules you have active. Now, most systems can handle one or the other reasonably well, and Vespa can handle both at the same time in one ranking step. Now let's go level deeper. There are basically 5 families of signals that feed into ranking. Behavioral signals. Now, these are what the users actually do. These are your clicks, your add to basket, the dwell time. Then you have the item signals. So this is what's true about the product. This includes stock level, margin, freshness, and user ratings. Then there are contextual signals. And this is what's true about the moment. So that's where you get into device, time of day, weather, or season. Then we have logistics. So this is really understanding if this order can even be fulfilled. So, which zone it ships to, what's the delivery SLA. And then finally, business signals. So this is what's the commercial intent. This is where you want to pull in promotions, specific vendor priority, any compliance rules. Now, in traditional systems, these get applied one after the other as overrides on top of a text result list. And in Vespa, they all feed into one unified ranking computation, which we'll talk about more later. Now, a key thing to note is that most systems can't use all signals. This slide shows some examples of the signals you should be incorporating into your search stack. Now, a typical enterprise search stack can handle, the basic 5 at the top, whether it's keyword matching, basic filters, static scores, as well as a few behavioral signals. However, anything dynamic like real-time stock, live weather, personalization vectors, query click machine learning models, these either require enormous engineering effort or it's simply not possible. And when we say near impossible without Vespa, this is more than just marketing language. It really reflects the architectural reality that swapping machine learning models without downtime or applying per user personalization tensors in real time requires capabilities that traditional search engines simply weren't built for. So what does Vespa bring that changes this? Well, there's three key things. First is the unified retrieval, and that's where we bring in the vector search, keyword search, and structured filtering. These aren't three separate systems that you stitch together like in traditional systems. It's one query pipeline. Second is scale. This is the same engine powering over 150 applications for Yahoo and many other global platforms. It's built for scale. And finally, the big one for today, machine learning inference runs in line with search. So this is not a downstream re-ranking step. It's not a separate service. It's right there in the same query. And that changes everything about what's possible. So now I want to hand it over to Zohar to dig a little bit deeper into Vespa's approach. Zohar?
Thank you, Bonnie. So yeah, let's review how Vespa streamlines the signal integration. Um, it can be done during ingestion for document level signals. It can be done during transformation and indexing. And at query time, it can be done during query enrichment and ranking. All of that within a single system. So document level signals are ingested into Vespa, and this includes like click streams, purchase, stock level, the catalog. They all flow into the same document and are stored with the product themselves. In-flight transformation happens via document processor while we ingest the data into Vespa. Custom logics that runs as the documents move through the right pipeline using this functionality. And this can be things like compute and embedding, leveraging Vespa compute. That can include enriching, the document fields, deriving an aggregate. Tensor on the side represent complex data modality and can be used to represent certain complex modality as a signal, like business rules. And they can be, multi-vector attributes. They can be sparse attributes, behavioral counters, all stored as tensors. And they're available on the document to the ranker in real time. Vespa also has attributes. Those attributes can be updated in real time, and these are signals that are truly live. And this includes, the stock, the price, the click counters, personalization tensors, which can represent a user cohort behavior towards a product. And those can be updated in less than a second. The ranker will see now the new value on the very next query. Now we also have real-time signal that only exists at query time. So the query itself can actually carry contextual signals that didn't exist a second ago. This includes weather, location, device, session intent. And also we can pass at query time, we'll discuss that later, business rules that can be injected as query parameter, like for example, to trigger promotions or boost certain type of items. All of this is consumed by ranking in real time. So this is where the document time attributes, which are, like we just discussed, are updated in real time. The query time live signals and tensor math all happen together inside one ranking expression on the node where data lives. And this is where what we call the fusion of all these signals. One thing to note is that Vespa allows you to do live machine learning model updates. And this enables a new model life cycle because machine learning ranking models can be swapped on a live system with no downtime and application redeploy. So what this really enables is imagine you have a training loop on freshly collected click data. You can retrain the learning to rank model and roll it out multiple times a day. And the model lifecycle moves to retrain weekly or quarterly into refresh multiple times a day. So the ranking really stays current with shopper behavior, right? So as we know, there's seasonal trend, there's certain type of events like weather event that could happen and which could modify the behavior on what you are going to sell that day on your site. And with this particular option, you are able to really surface what's going to matter to users in that current context. Um, so really, we can see that with Vespa, one unified system means that you can integrate all the signals that you care about, whether they're part uh, of the ingestion time, they can be live updated, through Vespa partial update, or they can be set at query time. And all of these reach the ranker and are applied in real time during retrieval. So there's no batch lag, there's no glue code, there's no external re-rankers. Now, let's take an actual example to see how this would really work, right? Um, let's say it's January and a shopper is in Denver, Colorado, and it's snowing. And they just type one word into the search bar. They type the word jacket. So without Vespa, most search stacks treats this question in isolation, right? So it might have some synonyms related to jackets, could do a semantic search related to jackets, and the search will return all kind of jackets, return lightweight summer jackets, spring jackets, with a mix of winter jackets. And the catalog isn't aware of the surrounding and the context of the search. There's no awareness of the weather location, um, the conversion eventually fails. The shopper leaves frustrated, and the missed conversion cost is invisible to the system. Condition can vary. The weather is unpredictable. That can, we can have periods in January where it could get all of a sudden warm, above seasonal temperature, and a fixed nightly catalog, or when you train your ML ranking model weekly, you cannot surface that. With Vespa, you can actually pass the current weather forecast as a query time signal along with the keywords. The location can also help determine the type of jacket that people in Denver would be interested in. Perhaps, they would be interested in more appropriate gear for skiing, but the location can also determine the pricing zone and inventory, right? So only show jackets that can actually ship in a timely manner to the customer using a price that is reasonable to them, right? And by adding this additional context, like, hey, it's a jacket and this is for Denver where it's snowing, the ranking expression will promote water resistant insulated, winter jackets to the top. And we can also take care of edge case the other way, right? Like if it's unseasonably warm for January, the same ranking expression can naturally surface lighter option instead. So really the system adapts, the rule don't change. For regional pricing, the ranker can apply different price per geography in the same query. You don't need to, have a separate hop for figuring out the pricing. And all of this requires zero engineering. There's just a few extra terms in a Vespa ranking expression. You need to be able to accommodate the signal, pass the signal, and incorporate them in your ranking. And you don't have to spin up a new microservice or start a new data science project. So really, weather and location are not stored on every product document. We can really see that these are contextual signal and they're injected at query time, and they're actually taken as an input to the ranking function. Okay, from signal to SERP. Um, Different signals belong on different time scales, and Vespa supports all three. There are really multiple ways to integrate signals. The first way is doing it in batch mode, which is the traditional approach. You can collect query result click pairs over a week, and you can retrain the model weekly and redeploy. This works well and is good for heavy, slow moving features like embeddings, 30-day popularity, return rate, etc. With Vespa's ability to update ranking models and ML models live, like we discussed earlier, you can shorten the cycle. So instead of doing this weekly, you can retrain and roll out maybe twice daily a model on the freshest data, reflecting the trends of the day. And this alone changes the loop. The model is always learning from the last few hours of shopper behaviors, not the last week. Secondly, doing indexing time. And here the time scale is from milliseconds to seconds. Really, only Vespa allows you this. And here in this category, we have signals that change continuously, not in nightly batch, right? And this includes streamed events like stock levels, price changes, click counters, add to cart counters. With Vespa partial update mechanism, only the change fields are rewritten in place in memory. The ranker sees the new value in less than a second and can literally apply them in real time. These fields are becoming inputs during re-ranking, right? So, and then we can apply rules like rank lower items that are low in stock or don't rank at all. Those are items that are out of stock, or boost items whose click through rate just spike. The third category of signals are the signals that only exist at the moment of the request, and these are query time signals. And the scale here is milliseconds. So the way this works is that at query time, we have the text and a bunch of user context and additional parameters. Those user context features can be the zone, the segment, the session, the weather, the device, etc. So to isolate the initial candidate set, we can do hybrid retrieval, like a BM25 for lexical signals that can be, more sophisticated, like proximity of terms, distance, etc. We can combine that with ANN, a nearest neighbor, along with structured filters to make sure we return, only relevant result. And all of this is done in a single pass, not three separate calls. Vespa leverages multi-phase ranking. So during the first phase ranking, we can use, a cheap computation during ranking, which can be the BM25 nearest neighbor search, to isolate the first candidate set. And during re-ranking, we can apply more expensive learning to rank machine learning models, which would apply business rule, propensity to buy. And finally, in a global phase, we can re-rank all over the fuse signal, fuse the signals that include, query time signal or the business rule that you want to apply. And finally, within millisecond, we can return a rank SERP with diversification and all your business rule applied. All of this in a single round trip. Now, let's talk a little bit about intent disambiguation with query click models. What this is about is the shopper own clicks are the highest quality signal of what they actually meant. And a query click model turns clicks into ranking. Let's walk through this example here. So a user types pink, and pink is kind of ambiguous. It can mean the singer Pink, the band Pink Floyd. It can be, any pink products like a shirt or a t-shirt. And the keyword matching alone cannot solve for this, right? As the next step, the search system can result, diversified result, right? Like a blended SERP, like Pink Floyd, pink colored items. And that's intentionally diverse. So the system doesn't yet know which intent to commit to. In step three, the user, let's say, clicks Pink Floyd. So that's actually what they meant. And the click is the key event. It's a verification signal that provides us the labels to train a model, right? So the query pink is now associated to Pink Floyd, and it's a positive example. And non-clicks or the other shown items are classified as negative, weak negatives. And multiplied across all shoppers, click patterns will reveal the dominant intent. Now, in this scenario, the model will learn from clicks. And with Vespa, you can collect, the tuples of the query, the result, and the click that can be trained, that can be used to train a re-ranking ML model. And the model will now be able to predict, given a query text embedding, a candidate set of features that can go, from text match, the popularity, any other attributes as location and the user context. We now generate click pairs that can form a learning to rank model. Now, once we retrain our model at the next query Pink Floyd is boosted, the retrained model goes live with no downtime, right? One thing to highlight here is the personalization tensor, right? So here, as you've seen in our previous demo, and we're going to demo to it again today, each click can append to a fixed size interaction tensors, right? Like to be able to register and record given user behavior. In this example, it can be, for example, the last 10 items that they clicked on. At the same time, we can have a document processor that that can compute the running average life, and we can store that personalization tensor and persist it in a user tensor. So the next time that user comes, we know exactly the preferences and the type of items that they're going to look at. So we know that next time that user comes and they click on pink, then we will have a Pink Floyd as a preference attribute that we have stored for this user. Storing a fixed size interaction tensor during the session will allow us to address a cold start problem, right? So initially we don't know anything about the user, but as they click through and we maintain that tensor live, we are able to very quickly personalize the result that we return to that user while he's literally browsing the site. Now, let's discuss how merchandising rules can be applied as dynamic signals, right? So in this example, business levers are expressed as query time signals, not code deploy. So essentially, merchandiser need to influence ranking constantly. This can be promotions, partner campaigns, margin target. The way this really works is that the product features like the margin, the brand, the category, they are document level signals and they live as attributes on the document and they can be updated in real time with no reindex. The application layer can inject during query time as query parameters additional signal reflecting those business rules, right? So in the first example, we can, for example, promote high margin SKUs during a sale without touching the code or the ranking model. The way this works is we can pass a margin weight at query time, and the ranking expression can become the base relevance plus the margin weight that we just passed multiplied by the attribute margin, which can be a scale value representing how much margin we are doing on that product, and automatically we will surface higher items on which we will boost higher items on which we have a higher margin. The same principle goes for sponsored and priority product, right? So the way this works is that a brand partner pays for placement in a specific category during a campaign window. Let's say it's a brand, a sports brand, and they want to promote running shoes. During the query time, we kind of inject, hey, this is the, as a tensor, for example, these are all the brands that are sponsorized. These are the category that they sponsorized, and this is the level of boost that we want to give to this various campaign, right? Like some campaigns might be more aggressive than others. And the ranking can take that as an input. And if the product matches any of the brands and category, it can actually give a higher boost coefficient. All of this happens in real time. It's self-gating. The boost only fires for matching candidates, so it never pollutes other queries. And when the campaign ends, we just stop injecting these parameters, and essentially the boost will have a zero value. Finally, another example is multi-objective ranking. Let's say we want to balance, revenue in terms of margin that we're making from a product versus the relevance of an item versus, the turnover of that item in terms of freshness, right? The same principle apply. The relevance can be the result of your hybrid search between BM25 and vector closeness. The revenue could be, an attribute on the margin times the price of the item, and the freshness could be, when was this item last added in stock, right? And same thing during ranking, you can assign weights to these different factors and surface higher, items that satisfied all these objectives with different weights. So essentially, ranking is a function. This function takes parameters. With Vespa, you can apply ranking in real time, and anything the business wants to control becomes a parameter to existing ranking function. We can be adjusted and can be modified in real time, and it doesn't become an entire data science project. With this, I will pass it over to Bonnie.
Okay, thank you, Zohar. So let's go ahead and take a quick look at a short demo just so you can see how this could look in action. Today, we'll demonstrate how Vespa integrates signals to power advanced product discovery, bringing together the key components of search, recommendations, user signals, and the product catalog, all in a single platform. This unified approach means everything works together and in real time without needing to stitch together separate systems. Let me show you what that looks like in practice. First, we'll start with document signals. Each item has both sparse and dense representations. What you're seeing here is a sparse representation generated purely from visual understanding using a vision language model. It captures details like color distribution, material type, how the item fits on the body, and other visual features, just as a human would perceive them. These representations form a kind of feature fingerprint for each item. And because Vespa can index and search over these in real time, we can instantly find visually and semantically similar products based on those features. Now let's take a look at user signals. We'll start by going into the user's profile. Now let's go ahead and tweak those preferences to show that this user likes green and yellow, but not red. Now, as you can see, the results adapt in real time. If we click on an item, we can see the recommended results also match the user's preferences. Now let's look at an example using dense embeddings, which will allow us to personalize the experience even more. I'll click on a set of earrings, and as you can see in the recommended results, the list also has been personalized using the dense embedding. Each time I click, I'm actually refining further and further for the types of items that my user is particularly interested in. So when, for example, I click on this, I start to see very, very similar items with a mix of emerald, which has the same shape, the same tone, as well as a mix of diamonds. Now coming back here, I can start liking certain items. Let's say I prefer a more matte color for an emerald. I'll start liking some items of a completely different style to what I demonstrated you earlier, and I'm going to turn on the dense personalization so you can see again personalization in real time. The signal is the same real time, but it's a different type of signal. Now let's go back to the user profile. As you could see earlier, we had discussed the green, yellow, and red, which is still in the user preferences, but now we're doing a dense personalization embedding. So the signal here comes as incrementing. If I take a closer look, this seems to be 256 dimensions of float values. Again, as a reminder, this is using proprietary embedding models from one of Vespa's partners, and this dense embedding allows us to represent with a great degree of accuracy all the nuances of an item that a user likes. So this is the key that you're able to do in real time with a very high level of granularity. And this is the power of Vespa's real-time engine, reacting to clicks, favorites, or filters in milliseconds. And with that, let me close the loop on what we've covered today with how Vespa solves the signal integration problem. So the signal integration problem is very real and it is costly. And again, this means that shoppers see irrelevant results, stale inventory, and missed personalization opportunities. Now, Vespa solves this through a single architecture that handles ingestion time and query time signals in the same ranking computation. Partial updates means stock, price, and personalization data is always current. There's no re-indexing lag. Machine learning models update live, and complex business logic like weather boosts, dynamic pricing, or merchandising rules is expressed in a few tensor expressions. And of course, the whole thing runs at production scale globally. So if you're fighting with a search stack that was built for documents, not signals, then this is the conversation to have next. Now, let's go ahead and take a few moments for some questions. So I will go ahead and see. So if you haven't submitted a question yet, at the bottom of your screen there, we have a Q&A portion. So there's still time to ask a question if you haven't submitted one yet. We do have a few, so I'll go ahead and start with the first question. So the first question is, you talk about machine learning ranking, but where do the machine learning models live in Vespa and how does the inference happen? So Zohar, maybe you can take that one.
Yes, that's actually an excellent question. So with Vespa, the machine learning model could be GBTT model or an NX model that you can that can be part of your application package along with the schema and some other component of your Vespa application. And when you deploy the application, what happens is that the model files are getting deployed at the contact node level. The reason why Vespa does that is to have the model inference happening as close to the CPU and close to where the data resides, because Vespa does ranking and apply those machine learning to rank model during retrieval, right? So that's the reason why they're located. Now, for Vespa, there are multiple phases of ranking. So some will happen at the content node level. So those one would be deployed there locally at the content node level, but they could also be deployed if they're part of a later phase on the content node, if that's what your configuration is.
Okay, great. I will move on to the next question. Can you provide more details on how multi-phase ranking works?
Yeah, that's a very good question. Multi-phase ranking for Vespa essentially allows us to do things fast, provide you low latency while not sacrificing accuracy, right? So the whole idea of multi-phase ranking is the first phase happen intertwined with retrieval. So let's say you have millions of products and items on your e-commerce site. And the first phase will isolate that to, let's say, the first 1,000 candidates, depending on the targets of your query. And that's going to be the first phase. And you want to use some cheap, cheaper computation type ranking methodology like a similarity search or BM25 in your first phase. The phase two is going to be a re-ranking based on the 1,000 candidate. Now, because you are only re-ranking at the local data node, contact node, the 1,000 candidate, you can use maybe a machine learning model or learning to rank model, which is a bit more expensive, like a GBTT model. And finally, the global phase, which is the last phase of ranking, happens on the container node level. So in this case, what's happening is that each content node individually is going to send the target hits. Let's say there are 100, and the global phase will apply your last model, learning to rank model, if you have any, to merge those results and only surface the top 100 from each content node.
Okay, great. Another question here. Does Vespa offer a solution to manage all the signals? And I can actually take that one. So Vespa is the search and retrieval platform, but we also have a commerce solution that is more focused on really tailoring that personalized experience. So it enables you to manage things like, the signals, do A/B experimentation and testing, and manage the ranking function. So that's something that we also offer. So feel free to reach out if you have more questions about that or you want to learn more about that.
There's one more
We got,
question on the Q&A, I think, Bonnie.
yes, yeah, this will be our last question. So is Vespa embedding similarity computed on co-located GPU? And I'll give that one to you, Sohar.
Yeah, that's a good question. So the similarity is computed locally at the content node level. For now, it's not using any GPU. It's going to happen using CPUs locally at the content node level and co-located, right? Like so, first phase, second phase ranking, where you are doing some sort of similarity measure, will happen on the content node level. The GPU right now in Vespa can be leveraged on the global phase at the container node level, right? Having said that, we are still, from a roadmap perspective, exploring ways to leverage GPU compute within the core Vespa engine. That work is still ongoing, and see where we can really grade the benefits of GPU to the maximum extent possible before rolling out those changes.
Okay, great. Looks like that was our last question. So I want to go ahead and say thank you, Zohar, for participating in this with me, and thank you all the attendees for sticking around. And if you have any questions, feel free to reach out. Have a great day, everyone.